Okay, hi everybody, I'm Dave Aronson, the Tyrannosaurus Rex of Codosaurus. Some of you may already know me from things like Nova, Python, DC Tech, and Ruby DCamp way back when. And tonight I'm here to teach you to kill mutants. So what on Infinite Earths makes mutation testing different from all the other testing techniques we know? The big difference is that most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is correct, at least in the sense of passing all its tests. Instead, mutation testing, I've got a notification and a way to get rid of, there we go. Mutation testing is looking for two other qualities. And in a typical code base, I think the more important one is that our test suite is strict. Now, you might be thinking, isn't that what test coverage is for? No. The only thing that test coverage tells us is that at least one test ran the code that it claims is covered. It tells us nothing about whether the correctness of the code had anything to do with whether any test passed or failed. So how can we tell if some code really is tested as opposed to simply run? As you might have guessed, that's where mutation testing comes in. To check whether our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. And when it finds such gaps, we can fill them in by either adding more tests or by expanding and improving some existing tests. When a lack of strictness usually comes from lack of tests, of course, but also from poorly written tests. The other thing that mutation testing checks for is that our code is what I call meaningful, so that any tiny little semantic change, as opposed to structural, stylistic, syntactic, and so on, will actually have a noticeable effect on the code's behavior. Lack of meaning usually comes from code being redundant or unreachable or otherwise just not having any real effect. And when we find it, the usual solution is to just get rid of it. Mutation testing puts these two together by checking that every tiny little change the tool knows how to make does indeed have a noticeable effect on the code's behavior, and that our test suite is strict enough that at least one test would notice that change and fail. Now that's the positive side, but of course there are some drawbacks. The first is that it's rather hard labor on the CPU, and therefore it can be rather slow. We certainly won't want to sit and wait while a mutation testing tool runs on our entire code base, at least for any non-trivial sized project. But we can let it run in the background, or while we're not even there, like over a lunch break for a smallish system, or maybe a weekend for a larger one. Also, many of the tools let us specify that we just wanted to check, some particular method or class or file or directory or whatever. And some of them even have some kind of incremental mode, so we can tell it just check what changed since the last time we ran the tool, or the last git commit, or the changes from the main branch. With these kinds of filtering, maybe we can tell it to just check the relevant changes over a much shorter break so that we can actually maintain our attention, sit there and watch it. Another drawback is that it's often not at all clear what to do about the results. It tells us that some particular change to the code made no difference to the test results, but what does that even mean? It can take a lot of interpretation to figure out what a surviving mutant is trying to tell us. They're usually trying to tell us that our code is meaningless and our tests are lax, but it can be difficult to figure out exactly how. Worse yet, it's sometimes a false alarm, because some change might not make any tests fail, that's often because it didn't really make a difference in the behavior in the first place. And even if some change did make a noticeable difference in the code's behavior, most programs contain a lot of code that we just shouldn't bother to test, like debugging traces and so on. Fortunately, many of the tools have ways to tell them, don't bother mutating this line, or again, this method, this class, this file, and so on. That's usually done with comments, though, which can clutter up the code, make it a little less readable. So how does mutation testing actually work, unlike this guy? First, our chosen tool will break our code apart into pieces to test. These are usually going to be our methods, or functions if you're not doing something object-oriented, whatever. Then, for each method, it'll try to find the tests that cover the method, and then make mutants from the method. To make the mutants, it looks closely at the function to see all the different ways it knows how to change it. And for each one, the tool will make one mutant with that one mutation. Once our tool is done making as many mutants as it can from one method, then it will iterate over the list. And now we get to the heart of the concept. This chart represents the progress of our tool. Now, the tools don't usually give us quite all this information, let alone so neatly organized, but I find it a useful conceptual model. For each mutant derived from a given function, or method, the tool runs the method's tests, but it runs them with the current mutant instead of the original method. If any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the tiny little change the tool made in order to create this mutant, in other words, its mutation, had a noticeable effect on the behavior, and our test suite was strict enough that at least one test did indeed notice that change and fail. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And that means that the mutant has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree. So this code becomes this abstract syntax tree, and then it traverses that whole tree looking for smaller subtrees, branches if you will, that represent our methods. And after finding them, it looks for each one's tests, but how does it do that? That usually relies mainly on us developers either annotating our tests or following some kind of naming convention. These manual techniques are sometimes supplemented or even completely replaced by the tool looking at what tests call what functions out of our code base. So it makes it a lot easier. Next, it makes the mutants. And to make mutants from an AST of a single method, it traverses that again, just like it did to the whole thing. But now, instead of looking for smaller subtrees like twigs or something to extract, it's looking for nodes where it can change something. Each time it finds one, and for each way it knows how to change that node, it will make a copy of that AST subtree representing that one method with that one node changed particular way. In other words, again, one mutant with that one mutation. Now, I've been talking a lot about changing things. So what kind of changes are we talking about? There are quite a lot. It could change a mathematical, logical, bitwise, or whatever category, other categories you may happen to have, operator from one to another, even across categories where the language allows. Fortunately, in the interests of speed, a lot of them will either just restrict or let you configure it to restrict how different of an operator it will apply. So you can tell it only stay within the category, so x times y would only be divided and minus and plus and exponentiation. Or you can tell it only try the opposite, so times would only become divided by. When the order of operands matter, it can swap them. It can change a comparison from one to another. It can insert or remove a mathematical, logical, or bitwise negation. It can remove an entire statement or expression. It can remove an if condition or a looping condition. It can replace a method's entire contents with just returning some constant or one of the arguments, if any, or raising a deliberate error, or nothing at all, in cases where the language allows that. In fact, removing the entire body is the basis of a particular form called extreme mutation testing, which is very, very fast, but of course nowhere near as thorough. It could change a value to some other value, such as changing 42 into any of these. Yes, I realize Python doesn't have quite all these constants, but you get the idea. And many more, but I had to stop somewhere. And it could change it to one of a completely different and potentially incompatible types, like changing a number into a, if I can quote Gollum, string or nothing. There are many, many more types of changes, but I trust you get the idea by now. Now, from here on, there are no more low-level details I want to add, so let's walk through some examples. We'll start with an easy one. Suppose we have a function like this. Excuse me, a method like this. Never mind why, it's just an easy example. So let's roll with it. Now think about what a mutant made from this might return, since that's what our tests would probably be looking at. It doesn't look like it would have any side effects unless somebody's seriously messed with those operators. Now, mainly a mutant of this could return results like any of these. Again, with some not really Pythonic constants. But anyway, again, many more, but I had to stop somewhere. And suppose that we have only one test, like so. This is a rather poor test, and I think at least one reason why is immediately obvious to a lot of you. But even so, most of these mutants would get killed by this test, the ones shown here in crossed out green. But addition, multiplication, and exponentiation in the reverse order will all still get us the right answer. So mutants based on those mutations will survive our current test suite. So how do we see this actually happening? When we run a mutation testing tool, it gives us a report, which will look kind of sort of roughly like this. The actual format and amount of context and so forth will vary enormously depending exactly which tool we're using. But semantically, the information will be more or less the same. And in this case, that is that if we change the method called power in the file demo.py at line 42 in any of 4 different ways, then all its tests would still pass. And then it goes on to tell us that those 4 ways are to change the method declaration operation to swap the arguments, change the method body to turn the exponentiation into addition or multiplication, or change the method body to reverse the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? We can tell from a glance at the code that it's probably not redundant or unreachable or otherwise meaningless code. The body's just one line, so once again, that's extremely unlikely unless somebody's seriously messed with the meaning of the operators. So it's most likely a test gap. And the question now boils down to, how are these mutants surviving? The usual answer is that they return the same value as the original function, or they have the same side effect, whatever it is that our tests are looking at. To determine how that happens, it helps to take a closer look at one mutant and attest it survives. So let's start with the plus mutant. Looking at the test, this isn't showing up very well, at least from my angle. Anyway, looking at the change together with the test makes it fairly clear that this mutant survives because 2 plus 2 equals 2, the 2. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run with the mutant code that would pass when run with the original code. What we need to do is make at least one test, use inputs such that x plus y is different from x to the y. For instance, we could add a test or change an existing test to something like asserting that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. But in addition, 2 plus 4 is 6, not 16. So this kills the plus mutant. Y'all see how that works? Okay, seeing a lot of nods out there. Good, good. Better yet, 2 times 4 is 8, which is also not 16. So this also kills the times mutant. You'll find that killing one mutant often kills others of the same function or method, whatever. But the pair of argument swapping mutants still survive because 2 to the 4th and 4 squared are both 16. That's not a big deal. We can attack them separately. No need to kill all the mutants in one swell swoop and be some kind of superhero about it. To kill them, again, we can add a test or adjust an existing test to maybe something like asserting that 2 to the 3rd power is 8. If we swap those around, 3 squared is 9, not 8. So this kills the argument swapping mutants. Better yet, 2 plus 3 is 5, 2 times 3 is 6, and both of those are, guess what? Not 8. So the times and plus mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. This isn't the only solution, though. Even if we stuck to single digits, there are lots of ways to skin that flirkin. This may make mutation testing sound pretty trivial, but this was a deliberately simple example. So let's look at a more complicated one. Suppose we have a method to send a message, like so. Send message uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping around to pick up where it left off until the message is all sent. A fairly common pattern. A mutation testing tool could make lots and lots of mutants out of this. But one of particular interest would be this, an example of removing a looping control. Now suppose that this mutant does indeed survive our test suite, which consists mostly of this. There's a little bit more that I'm not going to show you quite yet. dealing with setting the message size and then actually creating the message. But even without seeing that, what does the survival of the non-looping mutant tell us? If a mutant that only goes through the loop once acts the same as our normal code, as far as our tests can tell, then our tests are only making our normal code go through that loop once. Okay, so what does that mean? You'll find that interpreting mutants involves a lot of asking yourself, okay, so what does that mean? Often deeply recursively. In this case, I'll cut to the chase and tell you it's trying to say that we're not testing sending a message larger than send bytes can handle in one chunk. There are lots of ways that can happen, but we're only going to look at two possibilities. The most likely is that we simply forgot or didn't bother. And the obvious fix in that case is to deliberately do so. Send a message bigger than our chunk size. For instance, we have here a maximum chunk size of 10,000 bytes, and yet we're only testing within a 3-byte message. So the obvious fix is to just deliberately send a larger message, and with this kind of messaging we can just take our maximum chunk size, add any amount greater than 0, and send that bigger message, no problem. But now let's look at another possible cause and solution. Maybe we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes, and we test with a large, and yet the mutant survives. In other words, we're still sending the whole message in one chunk. What could be wrong with that? It sounds like a good thing to me. What is this mutant trying to tell us in this case? In this case, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this, and now a lot of other stuff is obviously redundant because it was only there to support the looping. If we rip that out, we wind up with this. And now the ultimate message is much clearer. The whole send message method may be entirely redundant. We can just use send bytes directly. Now, in real world code, okay, maybe not. Maybe there's some logging and error handling and so on that we can't, or at least shouldn't, shove down the stack into send bytes. But at the very least, the looping was redundant. Fortunately, when it's this kind of problem, the fix is clear and easy. Just rip out the extra jump the mutant didn't have. That will also make our code more maintainable by getting rid of useless cruft that's just getting in the way of understanding it. Now that we've seen a couple examples of spotting bad tests and redundant code, I'll answer a couple frequently asked questions. First of all, this all sounds pretty weird, deliberately making tests fail to prove that the code succeeds. Where did this whole bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool appeared in 1980 as part of Timothy Budd's PhD work at Yale. But it still wasn't practical on typical developer-grade machines of the time. And they didn't even have super hot gaming rigs and whatnot to try it on instead, like we do now. But it became practical in about the early 2000s or so, with advances in CPU speed, multi-core CPU, larger and cheaper memory, and so forth. So now it's practical even on fairly low-end, but still relatively modern systems like this 2020 MacBook Air, though at least with the M1 chip rather than the old Intels. Second, a more practical question. Where should we fit it in our development process? Mainly, I think it belongs at least here in the stage of getting your pull request or whatever your process uses approved to merge into the main branch, or again, whatever your process uses. You can set some standards for what you're willing to accept, like there should be no mutants on any new code, no surviving mutants on any new code, and no increase of them on old code or whatever. Ideally, this would all be automated as part of a CI pipeline that would get started automatically when the PR is created and stop it if this requirement or other requirements are not met. That said, I personally would also do it in the linting stage, where I run all kinds of quality assessment and improving tools to make sure that my code is as good as it can be within reason before bothering anyone else with it, making them slog through it. If you'd like to try mutation testing for yourself, here's a list of tools for Python. There are many, many other languages that have this. Don't worry too much about taking pictures, because the last slide has the URL for the whole deck. One warning, it's been quite a while since I've actually done mutation testing in Python, so some of these may be outdated and there may be some new ones. But at least now that you know about the concept, you can go look. To summarize at last, mutation testing is a powerful technique for making sure that our code is meaningful and our tests are strict. It's fairly easy to get started with in terms of things like setting up the tools and annotating our tests if need be, which may be tedious and time consuming, but at least it should be easy. But it's not so easy to interpret the results, nor is it easy on the CPU. But even if these drawbacks mean it might not be all that great a fit for our current projects right now, I still think it's just a really cool idea in a geeky kind of way. If you have any questions, we have about 2.5 minutes now, trying to stick to half an hour. And if you think of anything later, there's some contact information and the URL for the slides, complete with a full script, which I've mostly stuck to. So, any questions? Yes, Kai?
I have more of a comment, but I think your function will always fail because it doesn't return anything.
Oops.
But that's just a Python thing.
Let's see, which one would that be? The X to the Y? Yeah, maybe I forgot to stick the return keyword in there. Done a lot more Ruby than I've done Python, and especially more recently. So yeah, that's the kind of thing I might forget. But thank you. I will make sure, well, I will try to make sure to fix that next time I'm doing the Python version.
Use some AI and edit the video and,
Yeah. Yeah, have it edit the video, give me a nice six-pack and big biceps and everything, and much less gray hair.
Yeah.
Okay, Rami, you had a question?
I did. So, in your experience, what are the first steps on the journey towards getting your organization, your company, or whatever, to actually contemplate things like this when, like many minds currently saying, do we have time for tests?
Oh, okay. For those of you in the back who might not have heard the question, it boils down to how do we convince the company that take stuff like this seriously when they're currently reluctant to even just test. I assume they're probably doing some manual poking at it, but things like having developers waste time with unit tests and such. Yeah. That is a difficult question. First steps, I think, would be to get them to care about quality in general. If you can get any statistics on customer dissatisfaction due to bugs and time wasted due to rework due to bugs, whether the bugs were found by customers, the worst possible scenario, or even by QA if you have it, which I presumably not. But I've worked in some places that have QA, and yeah, we were even trying to cut down on the bugs that make it to QA, but they have to care about quality in the first place. And you basically have to make a financial argument, show them how much time and therefore how much money is being wasted. If you can come up with something like, we're wasting 100 hours a week across the team, and then multiply that by not just the salary, remember they're fully loaded compensation, not even just what they get, including the benefits, but all the overhead. That can make an impact. Any more questions? Yes, Brian?
Have you ever used it and found that like some framework or library is the cause of all your mutants or anything like that?
Theoretically, that's possible, but with most of the tools, they will differentiate between your code and your dependencies code. I suppose you could just check out the dependency's own repo itself and run mutation testing on it. If you're finding that you've got some dependency that you suspect is rather buggy, and you want to either fix it yourself, like open source, or tell the maintainers, hey, your thing is insufficiently well tested, shall we say, then this can help give you evidence. Any more? All right, we're at, okay, one last one from Kyle.
I was wondering if you could talk about like how you go about filtering the types of mutations that a system could apply, because you listed a bunch of them, but then you said there's much more. I'm just wondering, like, if you were to restrict it at all to certain ones, like how would you go about picking the ones that you restricted to?
Okay, well first the actual mechanics of restricting them is going to depend on exactly which tool, because some of them aren't that configurable at all. But if you are using one that is, I don't really know offhand which ones would be best bang for the buck. I think I would probably start small and test fairly obvious things, like have it do extreme mutation testing, have it try the opposite of all the operations, maybe let it swap operands when it matters, and maybe a little bit of knocking integer values up and down by one in cases where they're being compared to something. So you have to make sure you got your limits right. And if that's not yielding much fruit and you've got the time to let it run, then yeah, just keep expanding and see if it can find some more. You'll probably hit a point of diminishing returns eventually. Any more? All right, we are at 34 minutes, so thank you.
Thank you all for coming to our first talk meetup in a little while. It is PyDistrict tradition, such tradition exists, for folks who are able to go out for a couple of drinks or something afterwards. So if folks are interested and know good places